Welcome to Zero. I'm Akshat Rathi. This week, shark skins, plane wings, and novel things. One of the best things I get to do in my job is to visit early stage startups, full of passionate people coming up with the solutions to the climate problem. Some of them work with the kind of headline-grabbing tech you hear about all the time: batteries, carbon capture, and even nuclear fusion. But there's all sorts of weird and wonderful inventions out there which hope to fill in the blank spaces in the net zero puzzle.
What we've made here is inspired by shark skin. Yeah. It is much more simplified than actual shark skin. So they're running in this direction. Yeah. And if you run your finger across, you can hear that buzzing.
That's the voice of Henry Bilinsky, the founder of MicroTau. And the high-pitched noise you can hear is his finger running back and forth across a thin plastic film. This is the startup's innovation, a textured film that imitates shark skin to reduce drag on airplanes. To the naked eye, it's basically transparent. But when you look at it under a microscope, you can see these tiny ridges, known as riblets, that mimic the pattern seen on shark skin. Think about it like a high-tech wrapping paper, but for planes, all in the service of using less fuel to fly and thus produce fewer emissions. Aviation contributes about 2% of global emissions, and its share is expected to rise in coming decades, so solutions are badly needed. Henry is showing me around a dimly lit room bathed in orange light. This is the lab MicroTau uses to 3D print this film. Henry says the film can reduce fuel consumption on planes by 4%. Now, that might not sound like much, but if the film can be rolled out across every plane worldwide, the fuel savings and the emission savings would be huge.
So in 5-10 years' time, we'll all be flying on planes with our shark skin on them. But then we'll also be having them in the water, in marine applications. We're replicating the patterns that we find in nature. And sharks are step one and a big problem for us to solve with big impact. But there's a whole host of really interesting materials.
On today's episode of Zero, we hear from two startups I met in Australia in August. The companies are trying to solve very different problems, but both want to clean up existing industries. First, we'll hear from Henry at MicroTau about where he thinks shark skin fits into the future of air travel, and later in the episode, we'll meet Stephen Vassiloudis, the founder of Novalith, a company trying to introduce a lower carbon form of extracting lithium for batteries. MicroTau was founded in 2016, and last year it raised 5.6 million Australian dollars in a round led by the country's Clean Energy Finance Corporation. Then, in July, it got a $3 million grant from the Australian government, which will go to fund trials with the country's low-cost airline, Jetstar. I joined the startup CEO, Henry Bilinsky, at the company's office in the outskirts of Sydney earlier this year. I also talked to Ian Learman, the head of the Clean Energy Finance Corporation, in a past episode of the podcast. The link is in the show notes if you want to hear more. Henry, welcome to the show.
Thank you. Good to be here.
Now we're going to talk about shark skin being used for good things. Before we do that, how did you come to working on shark skin applications for stuff?
It was an unusual way to get involved. It came about from a global innovation challenge that the US Air Force Research Laboratory posted. It was actually late 2015 that they posted this challenge. And they were looking for ways to reduce their $8 billion a year fuel burn. And the lion's share of that came from their transport aircraft, so big, heavy planes, things like C-17s, C-130s.
Well, the Department of Defense in the US is probably one of the largest, if not the largest, emitter of greenhouse gases.
Yep. So I know the Air Force alone spends about $10 billion a year on fuel now. And so, yeah, we've got planes flying overhead to demonstrate it just for this podcast. We organize it. No, we're under the flight path here in Sydney, but it's a nice constant reminder of what we're focusing on. And so $10 billion a year in fuel, you're talking on the order of tens of megatons of carbon being emitted. So at that time, they were really just focused on reducing their fuel burn in terms of saving money and also a national security issue because, they're dependent on being able to burn that. So there was a global challenge. I responded to it.
As a researcher?
No, I was actually getting admitted as a lawyer at the time, but I do have a physics background. And so I was looking at these kind of online open innovation challenges. The thing I was interested in is whether you could find new problems to solve with old technologies, especially by looking to outside industries. So I tried a number of these open innovation challenges, and this Air Force one came out. They knew about this idea of shark skin and that the microscopic patterns that you find on shark skin have the effect of reducing drag, and that these microscopic patterns reduce drag, but they didn't really know how to practically implement them on a huge surface area like an aircraft. And so I proposed kind of modifying a computer chip manufacturing method called photolithography. It's a way of printing things that are even smaller than what you need for shark skin with light, and put that in, and frankly didn't expect to hear anything back, but was selected as one of 10 awards from around the world, then went and pitched at an Air Force base in Dayton, Ohio, where the Wright brothers are from, the Wright-Patterson Air Force Base. There was a whole process, but ultimately won a contract to build and develop and demonstrate this technology. And that's when I founded the company in 2016.
So shark skin looks pretty smooth. I've not touched a shark, but I'm assuming it's very small, the changes that you are trying to replicate.
You're right. So they do look smooth, and sharks are very efficient swimmers. And you would usually think that a smooth surface is the best way to move through air or water. What they're covered in, though, is if you do touch them, they feel more like sandpaper because they're these microscopic ridges on the skin of the shark.
Right.
Those ridges are known as riblets. So sharks have developed them over millions of years. We're the beneficiaries of that great R&D. But the first work sort of humans looking at this has happened a while ago, originally done by NASA, about replicating these microscopic patterns.
So you're kind of piggybacking off NASA's own science or US government's own science work, but actually showing them how to build it and apply it.
Yeah. So NASA did that original work. So they made them on sort of a millimeter scale, but knew that you need to get them down to the micrometer scale. So fractions of the width of a human hair is what we're talking about to get it to work in aviation. So yeah, we're definitely the beneficiaries of not just NASA, but a whole lot of work has been done in the intervening years throughout academia and different research institutions.
And so you proposed this idea of making this stuff, although you didn't have any equipment, you had never done it before.
No, I was Henry from Sydney, and I am very lucky that the US government, but also the entire advisory committee there took a punt on myself and also the team that I pulled together. So yeah, I definitely am lucky to work with very smart people on this too.
And so now 6-7 years on, you are making stuff.
Yes.
And we got a tour of your facility and there is light printing happening. But just walk us through, briefly the steps involved in making the stuff. And then what happens once you do make these films, right? They're basically plastic sheets.
Yeah, so essentially it's a prefabricated film that you stick onto the outside of a plane, very similar to other films that are already applied to planes that are usually done for advertising or graphical purposes. So the way that we manufacture, and that kind of is our core IP and differentiator, is this process we call direct contactless microfabrication, or DCM. That's basically this process where we grow the structures, these microscopic patterns. So again, these ridges spaced about half the width of a human hair, we grow them with light. So we get a material that cures when it's hit by ultraviolet light. We lay down a layer of this material. It will remain liquid or uncured until it's exposed. And then we have an optical system that projects that shark skin pattern into the surface and grows the structures from the bottom up. The reason why I'm being particular on that point is what's distinct from typical 3D printing is usually really 2D printing done over and over again. You print a layer in 2D and then you do it so on and so forth. We actually can print entire 3D structures only at the micro scale in a single exposure step through this process and this effect.
So explain drag and how exactly this thing reduces drag.
So drag is the force that a body moving through a fluid experiences. So a shark has to expend energy to push through the water, or a plane has to burn fuel to push through the air. If you can reduce that drag, you can reduce the amount of energy that you have to burn. The way that these structures work, it's counterintuitive. Usually a smoother surface is better when it comes to reducing drag. But what sharks have worked out is if you have these specific ridge designs, you can interact with a phenomenon that's known as hairpin vortices. So if you zoom down to that microscopic scale in what's called turbulent flow, so when the flow is all messy, which is most of the flow that anything experiences, especially planes.
I think one visual is, an incense stick. If you burn it in a closed room, you get this like nice stream. If you move your hand around, it just
becomes chaotic, and that's kind of turbulence, right?
Exactly right. So when it's all nice, clean streams of smoke, you can see that's laminar flow, where everything's ordered and predictable. And then eventually, if you wait long enough, the top of that will get all messy and swirl around, and that's turbulent flow. Now, on a plane or on a shark, most of the flow is turbulent flow. And if you zoom in small enough, there are these very predictable structures called hairpin vortices. They're kind of in the shape of a hairpin. Funnily enough, they're about the diameter of a human hair. They're very predictable according to your flow conditions. And they provide additional scrubbing and energy on that surface, which essentially means more friction drag, more drag that's applying to the surface that's moving through the fluid. But if you can make these ridges just narrower than the diameter of that vortex, then you can actually exclude it from the surface, and it doesn't fit in between the ridges and it only interacts with these very sharp peaks. The result of that is that you get a net drag reduction effect because they're not actually interacting with the surface completely. Again, sharks get the credit for coming up with this idea, and it works incredibly well. So with the material that we have made to date and sort of our current generation of product, we reliably get an 8% friction drag saving. That'll have a different impact depending on the application, but on a typical tube and wing aircraft, you've got half of your drag being friction drag, so that 8% becomes a 4% net efficiency gain. So 4% less fuel burned, 4% less carbon emissions.
Well, you give sharks credit. It's not like they were thinking about it. It's just that they kept swimming in the water, and the more efficient ones won out, and then they got evolved into the beasts that they are, beautiful as they are.
I can't claim to know the inner workings of sharks, but they definitely are the ones that came up with it. So whether they thought of it or not.
So what kind of impact do you think you can have?
So today, global aviation spends about $200 billion on fuel, producing about 1 billion tons of carbon. And we could be, with our current products, saving up to about 4% of that. On individual, say, wide-body aircraft, we can be saving on the order of $1 million of fuel a year and 3,000 tons of carbon. And that's where we're currently at. And the other thing which I referred to when I showed you the lab in the tour, we really want to leverage the fact that we can make new designs and improve those savings.
Yeah.
And we also work with the University of Melbourne. They'll be building us a dedicated testing facility so we can start rapidly iterating the different designs that we can make, test them in the testing facility and improve that performance. And we're nowhere near any sort of physical limit as to what kind of efficiency gains we can be getting when it comes to functional surfaces and how we can improve the efficiency of aviation. So we want to push that up closer to 10%.
And what will be required to pass? What would be a pretty strict regulatory environment?
Yeah, so you're right. Aviation is a highly regulated industry, which is great. That's why we're safely flying on planes and not worrying about them falling out of the sky. And so we need to make sure that we fit within that regulatory process. We have a great model for how we can get onto aircraft, which is the graphical films I referred to earlier. So they're already films that are up to spec and applied to aircraft and flown on aircraft regularly. So we're installing in the same procedures, the same way, the same kinds of materials and passing those material specs. And that's the method that we're using we've got some upcoming flight trials. So we just had a project announced with some funding from the Australian federal government, which is in partnership with Jetstar, which is our biggest low-cost carrier here in Australia. And so we're taking that approach by using their existing framework of how they get films on. And that's great for the purpose of flight trials and initial applications. When it comes to launching this and putting this on many aircraft and really having the impact that we want to have, we'll be getting what's called a supplemental type certificate, which is an approved change to an existing aircraft.
And these films which they put on for advertising, etc., they take them off after a year or two, if that. You're going to have to keep them on planes which last 10, 20 years.
Yes and no. You're correct. The graphical films are typically removed within, say, a year or so, but there are products out there that have flown for over 8 years. So there is precedent in terms of having them on for longer. That's about the period of time that we want our product to last. And the reason we're not looking at longer than that is there are very well-defined maintenance checks that are done on aircraft for the same reason of keeping them safe. And you'll have a heavy maintenance check, which, depending on the aircraft and how it's operated, could be every 5 to 10 years. And that's where all of the paint will be stripped off the plane and will be checked down to the core structure of the plane, and then it'll be repainted. So lasting any longer than that is not really relevant for our product. But you're right, we definitely want to make sure that we're lasting that period of time. The business case is still very much attractive, even if it was only a 2-year product, but we're looking to make that last as long as possible, again, to have that impact.
And on the tour, we saw the lab and the testing facility. It's relatively small for what you need to do now, but where are you going to manufacture at scale if you're going to cover entire planes with this material?
Yeah, so the facility that you saw here today, that core technology we talked about, the way that we manufacture, and essentially what we develop here are the materials and kind of the key manufacturing inputs to manufacture large amounts of product at scale. Those inputs go to a continuous roll-to-roll manufacturing process, and we currently work with different third-party manufacturers where we go and have access to their existing production lines. We're about to do another production run, on the order of, say, 1 kilometer's worth of material, which is plenty for us to do a couple of flight trials. And then when it comes to scaling up, that manufacturing, our first manufacturing scale facility will be here in Australia, but the volumes that we're talking about, we expect to be building these in locations in the geographies where close to the markets that we need to ultimately serve. So say we'll have something in Europe, something in the US is how we'll do this in the long term.
The applications, though, don't have to be just restricted to airplanes. Drag is a problem for all sorts of things. Anything that moves, really, whether it's in water or on the road.
Yeah, that's exactly right. Obviously, we're focused on aviation at the moment, and there is a reason for that. Aviation is a very hard to abate industry. There's $1 trillion of planes flying today, which aren't going to be thrown away anytime soon, burning about $200 billion worth of fuel and producing about 1 billion tons of carbon. So we're getting very clear signals that this is a problem that the market wants us to solve first. But we're also looking at other applications further down the line. So we can be applying this to ships, say cargo ships, to improve their efficiency as well. I had a couple of things.
Yes.
Because I listened to your episode about flying cars. I listened to that and I was like, oh, that's probably why you want to talk to us, because you're skeptical about the transition of aviation to
electric.
Exactly.
Yeah.
And I think that's a big part of what we're trying to solve.
Okay.
And something which I think is why we're getting a lot of traction in aviation. The entire industry is committed to net zero by 2050. And there is not a clear, easy shot to get there.
Yeah, I mean, that's true for many industries, but particularly true for aviation, yes.
And even your colleague you were talking to said he's bullish on electric aviation and hydrogen aviation, and best case scenario that solves short and medium haul flight. There is no way that it's going to be doing wide body or long haul flights. But the other thing, and the reason why I made reference to the fact there's about $1 trillion worth of planes burning fuel in operation today, not to mention all the planes that are being manufactured still to be burning fuel, is we need to think about something which has an impact in the next 5 to 10 years. We can't just sort of hold on for a new breakthrough in battery or hydrogen technology. I think it's very necessary. I'm very excited for those things to come online, but it's an even longer regulatory road to get new platforms on.
Oh, for sure. And even if you do get electric and hydrogen planes working, any amount of efficiency gain that you get for them, the easier their job becomes, because then you have to put fewer batteries on, you have to put less fuel on. So efficiency is this weapon that few people think of or use as effectively as you can use to get to net zero.
Yep. And so I think where we're coming at this is, in the near term, we want to have an impact on the existing global fleet. Every airline's committed to say 1.5% efficiency gains. They're planning to just buy new planes. We can be a part of that solution to not only help them achieve that, but save money in the process. You're not paying a green premium, you're saving fuel in the process. But as electric and hydrogen, alternative powered aviation comes online, they'll be doing really short hops initially. And if maybe an extra 5% efficiency unlocks LA to San Francisco, there's a huge impact there. And we really want to be able to help with that transition as we have these alternative aviation platforms coming online.
Well, thanks for the tour. Nice to see sharks in a better light than a lot of people think about sharks.
Sharks are great, absolutely.
Yeah.
Since recording this interview, MicroTau has begun flight trials of its technology and plans for it to be rolled out more broadly on commercial jets in 2025. After the break, to meet net zero, we need enough batteries for 1 billion electric cars, and lithium is a crucial part of that equation. Is there a cleaner way to source it? While I was in Australia, I also met up with Stephen Vassiloudis, CEO of Novalith, a company that wants to reduce the carbon emissions that come from extracting lithium. Like MicroTau, Novalith is another company that has raised money with the support of the Clean Energy Finance Corporation. First $2.5 million Australian dollars in 2021, and then it completed a $23 million raise in April this year. I met Stephen at the Novalith office in Sydney.
Now we're going to talk about lithium mining and what it is that Novalith, your company, is doing to make it more efficient and even maybe carbon negative, which is a bold claim. But before that, how do you come to do this?
So in terms of, I guess, the origin story, so I'm a chemical engineer by background. I worked in a number of industries prior to Novalith, oil and gas, conventional chemical engineering, tried to make things cleaner and greener. And that's really been the big push for me over the last decade or so. And that's what led to the genesis of Novalith. Looking at the way the world is moving, right? We desperately need to electrify. The only way for us to do that is by using lithium at large scale. And the conventional means of lithium production are not particularly quick, clean, or cost effective.
Well, most people won't know this because most people haven't thought about lithium mining. They've thought about lithium's use in batteries because everybody has a smartphone and they have lithium-ion batteries.
And now EVs is a big push as well, right?
Exactly. But let's go from the basics of how lithium is mined and processed.
Yeah, so in terms of lithium, you have kind of two main sources of lithium. So you have your continental brines, so the lithium triangle in South America. So that's Argentina, Chile, Bolivia.
And that's basically liquids that are found under the earth, which are very highly concentrated in different types of salts, including lithium in them.
Correct.
And so you just pull out a lot of liquid, you put it in these salt pans, let them dry, take what's left, which is usually some type of powder, and then make chemicals out of them.
Exactly. That's very much your brines, right? They, take the lithium chloride powder or slurry, ship it off to China to refine into a lithium chemical. The other way of getting lithium is from rock. And so the vast majority of kind of rock-based lithium, so about 60% of the world's supply, comes from Western Australia in the form of spodumene. And so that's a hard rock. There's other sources of lithium, so soft rocks, such in North America and Europe. But the vast majority at the moment is from that hard rock-based resource.
And we've got some spodumene here that you showed me. I mean, I've not been to a lithium mine, but the pieces of rock you're showing me are all different colored. Like there's green and there's white and there's purple and even yellow. I thought mine rocks would look lamer.
Yeah. Look, I think we're actually in a pretty cool game with the lithium rocks. The lithium rocks generally all look quite pretty. And there's, 101 different types of kind of lithium bearing ores. They all look pretty cool. I mean, except maybe the clays. The clays are, I guess, a bit boring, right? They just look like a clay.
And so you take either rock or brine, and then what do you have to do next?
So the conventional process is, once you've kind of mined it, you've then concentrated to increase the amount of lithium from, say, your 1 or 2% to, say, 5 or 6%. You then ship that spodumene concentrate to China. And about, 80 to 90% of the world's lithium is currently refined in China. All roads lead to China in the lithium game at the moment. And I think the world is trying to change that, but it'll take a little while for that to pick up. But yeah, so once it gets to the lithium refinery, depending on the source of lithium, there's a quite a complicated and long-winded chemical process. But in a nutshell, you heat it up. You hit it with a very, very strong acid, so sulfuric acid. And sulfuric acid uses sulfur, which generally comes off the back of, say, oil and gas, desulfurization.
And just so people know, sulfuric acid is one of the strongest acids there is.
Definitely, yes. It's not something you'd really want to leave out on the kitchen table. And if you are working with it, I mean, there's a lot of safety considerations that you need to take into account. And again, that's one of the things that we're trying to move away from is in terms of using quite a harmful chemical, not only for personnel, but also from the environment.
Yeah.
Even though lithium mines are located in places with relatively high concentrations, lithium only makes up a small percentage of all the material that is dug up. Steve told me it's only a few kilograms for every 1,000 kilograms of mined material. So to separate the lithium you want from the materials you don't want, miners use sulfuric acid. It does the job because it's highly chemically reactive, but that also creates a whole bunch of other problems. First, it's not selective, which means other metals contained in the mined material are also extracted alongside lithium, creating a complex chemical soup that you have to further purify. Second, it's toxic, so managing it and getting rid of the waste safely is expensive. Novalith's idea is to do away with sulfuric acid altogether and use carbonic acid instead, which can be made by mixing CO2 with water.
So when you mix CO2 and water, you form carbonic acid. It's the same thing if you're using a soda stream at home.
Yeah.
Right? But you don't think of it as an acid, right? You can drink it.
Yeah. But if you drink too much soda, your teeth go bad, and that's because it's acidic.
Correct. So don't drink too much soda as a general kind of like health disclaimer here. But yeah, you don't worry about the kids playing with it. You make it and it's, great to have with a slice of lemon. But under the right conditions, we can actually use that CO2 water mixture very, very effectively and efficiently to extract lithium from the lithium bearing ores directly as a lithium carbonate. And that's kind of like the little Novalith black box in our patent.
The lithium used inside lithium-ion batteries isn't pure lithium. Instead, it exists as a salt, either lithium hydroxide or what Novalith makes, lithium carbonate. In using carbonic acid to turn mined lithium to lithium carbonate, the startup can skip over the step where sulfuric acid is normally used. Because carbonic acid is a weak acid, it also produces less toxic waste. And what waste it does produce is much easier and thus cheaper to handle safely. However, to make a weak acid work as effectively as a strong acid, Novalith had to design a different process of extraction.
So you have the black box. Yes, that's the IP, but it's patented. So you can talk about what's public, right? What is it?
Yeah. So, feel free to look it up for those of you who do enjoy digging into patents. If you imagine putting, a little bit of spodumene in a glass of soda water on the table, not very much is going to happen, right? You will form a lithium carbonate, but we'll be talking about this in, say, 3 years' time. And so with our process, the way we've managed to do this and actually found that it works really, really well is by changing temperatures and pressures. And so under a very kind of strict set of conditions, we find that we can very effectively extract that lithium. And the other thing we've looked into is the type of reactors that we're looking to use. So going to chemical engineering, again, there's 101 ways to do something. We found for our process that a fluidized bed reactor works really, really well. We can get great extraction efficiencies and control that mass transfer, which is what we refer to as.
Fluidized bed reactor, which as a chemical engineer, I know what it is, but now that I think about it, it's a really interesting name because it sounds like a massage table.
Yeah. Yes. No. Well, to be fair, you can kind of imagine it, right? So if you get a straw and you kind of blow bubbles at the bottom of a glass filled with a bit of sand, right? You're effectively making a fluidized bed reactor. And so you can see the bubbles kind of passing through the sand and it's all kind of jiggling about and doing its thing. And that's really what we're doing, just at a larger scale.
You're massaging the spodumene with lots of acid.
Yeah. To get our lithium carbonate.
But you also made this bold claim saying, well, we can make carbon negative lithium, which you're going to have to explain. So A, what is the carbon cost of lithium? Why is there a carbon cost to lithium? And how is it that you're going to negate it?
Yes. So in terms of that, well, we're currently doing a bit of work on confirming whether we can truly be carbon negative, but that's definitely our goal. Given that we use CO2, there's a really good chance of us achieving that goal. And so in terms of, I guess, the relative carbon intensity, right? If you look at the conventional process, you find that the vast majority of CO2 is emitted in that middle piece, so the chemical refining piece.
Yeah, it's interesting. People would think mining it, which requires a lot of energy, then moving it, then putting it either on trains or ships would be the biggest carbon cost. But actually, it's the chemicals, it's the treatment of the ore that is really carbon intensive.
Definitely. And it's the productions of the chemicals. So in the production of the sulfuric acid you need for your process, you're producing a ton of CO2. And so when we compared Novalith's technology to the conventional, and the conventional sitting between, say, 15 and 20 tons of CO2 per ton of lithium chemical, and it is jurisdiction specific, we were less than half of that. And it's already, well on the way to being carbon neutral, carbon negative.
Yeah, still a ways off.
The carbon negative part of Novalith's claim is still just theory. Carbonic acid can be made by mixing water with CO2 that has been captured from the atmosphere. The acid can be combined with waste metals from the lithium ore to form carbonates that can be stored underground, effectively locking the CO2 out of the atmosphere forever. This is something that is already being done by carbon removal companies Climeworks and Carbfix in Iceland at a small scale. So the theory does work. But to make carbon negative lithium, Novalith will have to store away more carbon dioxide than produced by the rest of the process. And I'll remain skeptical till I see the results.
So for spodumene, the way we can reduce the carbon intensity is by using greener sources of power, greener sources of electricity. At the moment, everything is coal, diesel. It's really dirty in terms of the power. Looking forward, we can significantly decrease the carbon intensity by using greener sources of energy. And then further to that, if we do have these carbonatable materials, right? So effectively the spent or the stuff that goes to waste, if we can add value to that by carbonating that, using either CO2 emitted by the power plant that the mine is are currently using to power its operations. There's a lot of conventional industry that needs a place to put its CO2, and we can help them store that CO2 and fix that CO2 whilst producing a very, very important and high-value lithium chemical product.
And we should acknowledge that while lithium has a carbon cost and it's substantial, the amount of carbon it avoids through the use of batteries in electric vehicles is much, much greater. But if you're going to scale green technologies, we ought to be much more careful about the carbon cost of building those technologies.
I completely agree. And that's what we need lithium, right? I mean, if you're looking at the relative carbon reduction or, negation, if you like, of transitioning towards an electric future, I mean, it is gigatons, several gigatons. It is tremendous, and we need to get there. Our thesis is we need lithium. We need it now, well, yesterday, to be honest. We need it cost effectively, but it has to be environmentally friendly. There's no point in using technologies which really kind of use the bones of old dinosaurs, right, to kind of prop up this green future. And so that's it. We have to try and make it as sustainable as possible to, really be part of that same ethos that we're kind of pushing towards.
And so we got a tour of your facility, and you've done this at a lab scale. So you're making kilograms of this on a day-to-day basis. But of course, we're talking tons here. And so how many years before you have thousands of tons in production using this method?
So we're sitting at kind of like kilo scale, right? We've done our lab and benchtop testing, and that's taken us 2 years to get to the stage where we're now confident in scaling up to our pilot plants. And so this year, we're currently building our pilot plant facility in Alexandria and Sydney in Australia, and we'll have that kind of commissioned and operating by the end of this year. Multiple pilot plants on site, producing tens of kilos of lithium chemical per day. So if things go the way that we were planning them to, we will have our first facility, our commercial demonstration plant, operating by 2026, 2027. And then scale of that will be between 1 and 5,000 tons per annum.
And where will it be based? Very
good question. So if you're looking at where lithium is primarily based, so Western Australia has a tremendous amount of spodumene. But the US, right? The US is pushing very, very hard into onshoring its critical mineral supply and really supporting this battery production in our electric future. And at this stage, it's looking like either US, there's a lot of lower quality lithium resources and there's tons of lithium in general, right? Which they need to find a better way to process. Or Western Australia, which is where the vast majority of kind of the hard rock lithium comes from at the moment. There's a lot of support from the government in the US, which is very attractive for not only us, but anybody looking to hasten that transition. And so if we can get support from the US, and again, given the criticality of lithium in general, I think we will be able to. It makes a lot of sense for us.
Well, thank you and good luck scaling up.
No, thanks very much for having me. It was great.
Thank you for listening to Zero. If you liked this episode, please take a moment to rate or review the show on Apple Podcasts and Spotify. Share this episode with a friend or with someone who is scared of sharks. Get in touch at zeropod@bloomberg.net. Zero's producer is Oscar Boyd and senior producer is Christine Driscoll. Our theme music is composed by Wonderly. Special thanks to Kira Bindrim and Luke Mills. I'm Akshat Rathi, back next week.